somewhere above the Earth right now, in the crushing cold of interstellar space. There is a place with no air, no dust, and no molecules for millions of kilometers in every direction. If you screamed there, nothing would carry the sound. That much is true. But ask a physicist a stranger question. Not whether sound can travel through empty space, but whether empty space itself is truly empty. The answer, once you look closely enough, is no. And that single word unravels one of the strangest ideas in modern physics. Long before quantum mechanics existed, the question of whether true emptiness could exist at all was already a source of fierce debate. Aristotle argued, more than 2,000 years ago, that nature abhors a vacuum, a principle later known by its Latin name, holographic, holding that empty space was not merely rare, but logically and physically impossible. Since Aristotle believed motion itself required a surrounding medium to push a body along and to rush in behind it. This idea dominated natural philosophy for roughly 2,000 years, shaping everything from the design of pumps to theological debates about the nature of the created universe. It was not seriously challenged until the 1640s, when the Italian physicist Evangelista Torricelli, a student of Galileo, filled a long glass tube with mercury and inverted it into a dish of the same liquid. Watching as the mercury column dropped slightly and left an empty space at the sealed top of the tube, a space with no air and no visible substance of any kind. Now recognized as the first deliberately created and scientifically documented vacuum, the same basic principle behind the mercury barometer still used today. A decade later, the German scientist and mayor of Otto von Guericke staged a now famous public demonstration, joining two large bronze hemispheres together, pumping the air out from between them, and showing that teams of horses harnessed to either side could not pull the hemispheres apart. A dramatic and visceral proof that emptied space was not merely a theoretical curiosity, but a genuine physical state with real, measurable consequences. In that case, the ordinary pressure of the surrounding atmosphere pressing the hemispheres, together with tremendous force once the air between them was removed. These early experiments settled the ancient debate about whether a vacuum could exist at all, but they left open and could never have anticipated the far stranger 20th century question this documentary has been exploring: whether the vacuum, even once emptied of every last molecule of air, might still be filled with something else entirely, something with no mass, no charge, and no classical presence of any kind, and yet with real, measurable physical consequences of its own. For most of the history of science, the vacuum was treated as a stage. It was the backdrop against which stars burned and galaxies spun, but it was assumed to have no properties of its own. Isaac Newton pictured space as an empty container, fixed and featureless, existing only to hold matter in place. Even after Einstein reshaped our understanding of space and time into a single flexible fabric, the vacuum was still imagined as the absence of everything, a mathematical zero. But somewhere in the 1920s and 30s, as quantum mechanics matured, physicists began to notice that zero was not quite what the equations were telling them. The trouble started with a simple question: what happens to a field, like the electromagnetic field, when you remove every single particle from a region of space? Classically, the answer is obvious. The field should vanish completely. There is no charge to generate it, no current to sustain it, so there should be nothing left to measure. But quantum mechanics does not allow for that kind of certainty. At the heart of the theory sits the Heisenberg uncertainty principle, And one of its lesser known, but far more unsettling consequences applies not just to the position and momentum of particles, but to the value of a field and its rate of change over time. You cannot pin both to exactly zero at once. If you try, the uncertainty principle pushes back, and the field is forced to fluctuate, even in what we call its lowest possible energy state, the state we call the vacuum. This is not a philosophical nicety. It has a name, zero-point energy, and it means that even a perfect vacuum, stripped of every atom and every photon we know how to remove, still seethes with residual activity. The name itself carries a small piece of history worth knowing. The term was introduced by the German physicist Max Planck in 1911, only a few years after his original 1900 proposal that energy is exchanged in discrete packets, or quanta. A proposal that launched quantum theory in the first place, but that Planck himself, notably, spent years afterward trying to reconcile with the classical physics he had been trained in and never fully abandoned. Planck's original 1911 suggestion was tentative and somewhat different in detail from the modern understanding. But the core intuition, that a quantum oscillator can never be brought to a complete standstill even at its lowest possible energy, turned out to be exactly right, and was placed on far firmer mathematical footing over the following 2 decades as quantum mechanics itself matured through the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others. By the time quantum field theory extended these ideas from single, oscillating particles to entire fields stretching across space, the zero-point energy of a quantum oscillator had become the zero-point energy of the vacuum itself, summed, in principle, over every possible mode of every quantum field in existence. An idea whose experimental consequences, as we have already seen through the Casimir effect and the Lamb shift, would not be confirmed in the laboratory until decades after Planck's tentative first guess. The fluctuations are tiny. They average out to nothing over any macroscopic distance, and they do not violate the conservation of energy because they borrow and repay so quickly that no permanent energy is created. But they are real, and by the middle of the 20th century, physicists had found ways to make their effects visible in the laboratory. The idea that took hold in these decades became known, somewhat playfully, as the sea of virtual particles. Quantum field theory describes every fundamental particle as an excitation of an underlying field that fills all of space. The electron field, the photon field, the quark fields. Each one stretches across the universe, and particles are simply ripples moving through them. In the vacuum state, these fields are not perfectly still. Because of the uncertainty principle, pairs of particles and their antiparticles can appear for an instant and then annihilate again, borrowing energy from the field for a duration so brief that it evades direct detection according to the time-energy version of the uncertainty relation. An electron and a positron might flicker into being and vanish again in a fraction of a second. A photon might do the same. These are called virtual particles, not because they are fictional, but because they cannot be observed directly the way a real, freely propagating particle can. Their existence is inferred from the very real effects they leave behind. The mathematical framework that makes all of this possible did not arrive quickly or easily. Quantum electrodynamics, the theory of how light and matter interact at the quantum level, was pieced together across the 1940s by 3 physicists working largely independently of one another, separated by an ocean and, for a time, by war. In Japan, Shinichiro Tominaga developed a version of the theory grounded in a careful, covariant treatment of time. In the United States, Julian Schwinger built an extraordinarily rigorous, mathematically dense formulation using the tools of operator field theory. And also in the United States, Richard Feynman took an entirely different approach, one that traded some of Schwinger's mathematical formalism for an intuitive, almost cartoon-like visual language, in which every possible interaction between particles could be represented as a diagram, now known as a Feynman diagram, with lines representing particles and vertices representing the moments they interact. It was later shown, largely through the work of Freeman Dyson, that Feynman's diagrammatic approach and Schwinger and Tominaga's more formal approaches were mathematically equivalent, two different languages describing the same underlying physics. All three men, Tominaga, Schwinger, and Feynman, shared the Nobel Prize in Physics in 1965 for this work that had to overcome a serious mathematical obstacle before it could be trusted at all. Early, naive attempts to calculate the small corrections virtual particles introduce into the properties of real particles kept producing infinite, nonsensical answers, a crisis that threatened to derail the entire theory in the 1930s and early 1940s. The solution, a technique called worked out carefully by Schwinger and Dyson through the late 1940s, involved recognizing that certain quantities appearing in the raw equations, including the electron's own mass and charge, were not directly observable in isolation, and could be redefined in a mathematically consistent way that absorbed the troublesome infinities, leaving behind finite, testable predictions that matched experiment with extraordinary precision. Renormalization struck some physicists at the time, including Dirac himself, as an inelegant, almost embarrassing patch rather than a genuine solution, and debates over its deeper meaning continued for decades. It was not until the 1970s, through the work of Kenneth Wilson on what is called the renormalization group, that physicists developed a fuller, more physically satisfying understanding of why renormalization works, connecting it to the general idea that physical theories, including our theories of the vacuum, are properly understood as effective descriptions valid over a particular range of scales, rather than as final, complete statements about reality at every scale down to zero. A lesson that applies directly to the open questions about Planck-scale physics and vacuum elasticity explored throughout this documentary. What makes the story relevant here is that Feynman diagrams did more than simplify calculations. They gave physicists an intuitive picture of the vacuum as a place of constant, silent activity, where, even in the absence of any real particle, diagrams could be drawn showing virtual particles briefly looping into and out of existence, contributing small but calculable corrections to the properties of real particles nearby. These loop diagrams are not decorative. They are essential to getting quantum electrodynamics right, and the theory's predictions, including the magnetic moment of the electron, have been confirmed by experiment to a precision better than 1 part in a trillion, making quantum electrodynamics arguably the most accurately tested theory in the history of science. Every one of those loop diagrams is, in a very real sense, a picture of the vacuum's own restlessness, translated into a precise mathematical statement that experiment has repeatedly confirmed. One of clearest of those effects is named after the Dutch physicist Hendrik Casimir, who, in 1948, predicted something that sounds almost like magic. Take 2 uncharged, perfectly conducting metal plates and place them extremely close together in a vacuum, separated by a gap of only a few hundred nanometers. Classically, nothing should happen. There is no electric charge on the plates, so there should be no force between them. But Casimir showed that the plates would restrict which virtual photon wavelengths could exist in the gap between them, while the vast, open space outside the plates would allow virtually every wavelength. The imbalance in the pressure of these virtual fluctuations produces a real, measurable, attractive force pulling the plates together. It was a bizarre theoretical prediction that sat mostly unverified for decades, because measuring such a tiny force required extraordinary precision. It was not until the 1990s, particularly through the careful work of physicist Steve Lamar, that the Casimir force was measured with the accuracy needed to confirm Casimir's original calculation to within a small margin of error. Since then, the Casimir effect has been measured repeatedly, refined, and even exploited in the emerging field of nanotechnology, where engineers must account for it because it can cause microscopic machine parts to stick together simply from being close enough for the vacuum's structure to press them into contact. If you find yourself surprised that too, ordinary metal plates can feel a force generated by nothing more than restricted geometry in the vacuum. It is worth bookmarking this moment, because the rest of the story only gets stranger from here, and it helps to have that first surprise fresh in mind as a reference point for everything that follows. This is the first hint that the vacuum has properties, not properties in the everyday sense of temperature or texture, but statistical, structural properties that can be measured, calculated, and in some cases engineered. If two metal plates can feel a force generated purely by restricting which vacuum fluctuations are allowed to exist between them, then the vacuum is doing something. It has a kind of texture, after all, even if that texture is nothing like the textures we experience with our hands. Physicists sometimes use a vivid, if imprecise image to describe this state of affairs. They call it quantum foam. The phrase was coined by the physicist John Wheeler in the late 1950s, when he was trying to describe what happens to the geometry of spacetime itself at extraordinarily small scales. Scales far beyond anything we can currently probe directly near what is called the Planck length, a distance of roughly 1.6 times 10 to the negative 35 meters. At that scale, Wheeler argued, the smooth, continuous picture of spacetime that general relativity gives us should break down. Quantum fluctuations should become so violent that the very shape of space and time would churn and froth like the surface of a boiling sea, constantly generating and erasing tiny wormholes, bubbles, and distortions in the geometry of the universe. This picture remains speculative. No experiment has ever probed distances anywhere close to the Planck scale, and it may be that spacetime is not quantized at all in the way Wheeler imagined. But the phrase quantum foam has since drifted into more general use, often applied loosely to the broader idea of a vacuum that is not silent and static, but alive with fleeting quantum activity even at scales far larger than the Planck length, in the more modest and much better understood sense of 0 point. Fluctuations in ordinary quantum fields. Wheeler's quantum foam was never meant as an isolated idea. It emerged from his broader effort, alongside collaborators, including Bryce DeWitt, to understand what happens when you try to apply the rules of quantum mechanics, not just to particles and fields living inside spacetime, but to the geometry of spacetime itself. This effort, sometimes called canonical quantum gravity, eventually produced the Wheeler-DeWitt equation in 1967, a notoriously difficult equation that attempts to describe the quantum state of the entire universe's geometry at once, and which remains, to this day, a subject of active interpretation and debate, since it famously appears to describe a universe with no explicit time variable at all. a puzzle known among specialists as the problem of time. Wheeler's foam picture was one attempt, largely qualitative, to give physical intuition to what such a quantum geometry might look like up close, and it has since been picked up, refined, and reinterpreted by several competing modern approaches to quantum gravity, each of which paints a somewhat different picture of what happens at the Planck scale. Loop quantum gravity, developed from the 1980s onward by physicists including Carlo Rovelli and Lee, proposes that space itself is built from discrete, quantized units, tiny loops of gravitational field that weave together into what is called a spin network, suggesting that at the smaller scales, space is not smooth and continuous but granular, like a fine mesh. String theory, developed from a different starting point in the late 1960s and matured considerably through the 1980s and 1990s by physicists including Michael Green, John Schwartz, and Edward Witten, proposes instead that the fundamental constituents of reality are not point particles at all, but tiny, vibrating one-dimensional strings, with the specific vibrational pattern of each string determining which particle it appears to be, and with gravity emerging naturally as one of the vibrational modes available to a closed string. Neither of these frameworks has been experimentally confirmed, and both make predictions, where they make any testable predictions at all, that require energies or precisions far beyond what current particle accelerators or astronomical instruments can reach. This is worth stating plainly, because popular science writing sometimes blurs the line between these serious, mathematically sophisticated but experimentally unconfirmed research programs and looser, less rigorous speculation. Loop quantum gravity and string theory are taken seriously by large communities of working physicists, precisely because they are mathematically consistent, internally rigorous frameworks that reduce to known, tested physics in the appropriate limits, even though neither has yet produced the kind of direct experimental confirmation that would elevate it from a leading hypothesis to an established theory. It would be a mistake to assume that the Planck scale, roughly 19 orders of magnitude smaller than the nucleus of an atom, is simply too small to ever probe experimentally, even indirectly. Physicists have found genuinely clever ways to search for faint traces of Planck-scale physics using signals that have traveled across enormous cosmic distances, on the reasoning that even an extraordinarily tiny effect, accumulated over billions of light years of travel, might eventually become large enough to detect. One of the most promising approaches has involved gamma-ray bursts, the extraordinarily energetic explosions typically associated with the collapse of massive stars or the merger of neutron stars, that briefly outshine entire galaxies and send bursts of high-energy photons racing across the universe toward Earth. Some versions of quantum foam models predict that if spacetime really does have a granular, foam-like structure at the Planck scale, then photons of different energies might travel at very slightly different effective speeds as they pass through this foam, with higher energy, shorter wavelength photons interacting more strongly with the fine-grained structure than lower energy ones, causing an incredibly tiny lag to build up over a sufficiently long journey. Missions, including NASA's Fermi Gamma-Ray Space Telescope, launched in 2008, have used precisely timed gamma-ray burst observations to search for exactly this kind of energy-dependent time delay, comparing the arrival times of high-energy and low-energy photons that were, according to the standard model of these explosions, emitted at essentially the same instant billions of years ago. So far, these searches have found no convincing evidence of any such delay, and have instead placed increasingly stringent limits on how large any Planck-scale departure from ordinary, smooth spacetime could possibly be, limits that in some cases already rule out the simplest versions of certain quantum foam models, forcing theorists to either abandon those specific proposals or refine them into forms with more subtle, harder to detect signatures. This is precisely the kind of quiet, unglamorous experimental progress that rarely makes for a dramatic headline, but that steadily narrows the space of viable theories. And it stands as a useful reminder that even the most exotic-sounding ideas explored by theoretical physicists, including the picture of spacetime as a quantum foam, are not exempt from the ordinary discipline of experimental testing, and can be, and regularly are, constrained or ruled out by careful observation. Precisely the opposite of unfalsifiable speculation, floating free of any connection to evidence. A related and equally rigorous line of testing involves what physicists call Lorentz invariance, the principle central to both special and general relativity, that the laws of physics look the same to all observers regardless of their motion or orientation in space. Many proposed quantum gravity theories, in their effort to describe a granular or foam-like spacetime at the smallest scales, predict tiny violations of this principle, effects that would be essentially undetectable in any everyday laboratory experiment, but that might, in principle, produce measurable anomalies in extremely high energy or extremely long baseline observations. Physicists have tested this using an impressively wide range of methods, including precision studies of how cosmic rays, some of the highest energy particles ever observed, propagate across the galaxy. Laboratory experiments using ultra-stable atomic clocks and optical cavities to search for any directional dependence in the fundamental constants of physics, and detailed studies of neutrino oscillations, the strange quantum phenomenon in which neutrinos spontaneously change from one type to another as they travel, which can be exquisitely sensitive to any subtle departure from perfect relativistic symmetry. Across every one of these tests, conducted by numerous independent research groups using entirely different methods and instruments, ordinary relativity has held up without exception, and any Planck-scale violations of Lorentz invariance, if they exist at all, must be smaller than what our current instruments, remarkable as they already are capable of detecting. This growing body of null results does not prove that spacetime is perfectly smooth all the way down to the Planck scale, since a small enough effect could always be hiding just below the current threshold of detection. But it does mean that any successful theory of quantum gravity, including any framework hoping to explain a genuine elasticity of the vacuum, must be constructed carefully enough to reproduce ordinary, unbroken relativistic symmetry at every scale we have so far been able to test, a significant and non-trivial mathematical constraint that has already eliminated several once theoretical proposals over the past 2 decades. It helps to be precise about what part of this picture rests on solid, experimental ground and what part remains a hypothesis awaiting better evidence. Zero-point energy in quantum fields is not speculative. It shows up in the Casimir effect. It shows up in the tiny but measurable shift in atomic energy levels called the Lamb shift, first measured by Willis Lamb and Robert Rutherford in 1947, and it shows up in spontaneous emission, the process by which an excited atom eventually releases a photon and drops to a lower energy state, seemingly at random. All of these phenomena are explained with remarkable precision by treating the vacuum as a quantum state with fluctuating fields rather than as literal nothingness. Quantum electrodynamics, The theory built on this foundation is one of the most rigorously tested frameworks in all of science, verified to more than 10 significant figures in some predictions. So when we say the vacuum fluctuates, we are not describing a fringe idea. We are describing the mainstream, well-confirmed behavior of quantum fields. What remains speculative is the leap from these confirmed fluctuations to a literal, physical medium with a texture like a fabric or a fluid, through which something analogous to sound could propagate the way pressure waves move through air or water. This is where the story gets genuinely interesting, because rather than staying purely theoretical, physicists have actually built laboratory systems where something very much like sound moving through a quantum vacuum can be measured directly. They just had to build their own miniature universe to do it. To understand how, we need to talk about a strange and beautiful branch of physics called analog gravity. The idea traces back to a paper published in 1981 by the Canadian physicist William Unruh, who had been thinking hard about one of the most famous unsolved puzzles in theoretical physics: the behavior of black holes according to quantum theory. In 1974, Stephen Hawking had shown, through a combination of general relativity and quantum field theory, that black holes should not be perfectly black after all, due to the same kind of vacuum fluctuations we have been describing. Pairs of virtual particles can appear near the event horizon of a black hole. Occasionally, one particle of the pair falls into the black hole while its partner escapes. And from a distance, this looks exactly like the black hole is emitting a faint stream of radiation. This is Hawking radiation, and it remains one of the most important theoretical results in modern physics, even though it has never been directly observed. Because for any black hole of stellar mass or larger, the predicted temperature of this radiation is so low that it is utterly swamped by the cosmic microwave. Background: Unruh's insight was that you do not need an actual black hole to test the mathematics behind Hawking's prediction. What matters, mathematically, is having some kind of horizon, a boundary beyond which waves cannot propagate back against a flow, in a real black hole. That flow is spacetime itself falling toward the singularity faster than light can escape once you cross the event horizon. But Unruh realized you could create an analogous horizon using something far more down to earth, a fluid moving faster than the speed of sound within itself. If you have a river flowing toward a waterfall, and the current accelerates as it approaches the edge, there comes a point where the water is moving downstream faster than sound waves can travel upstream through that water. Beyond that point, no sound wave generated downstream can ever propagate back past it. That boundary is a sonic horizon, and mathematically, the equations describing how sound waves behave near a sonic horizon in a moving fluid are strikingly similar to the equations describing how light behaves near the event horizon of a black hole. This was a remarkable idea, but for a long time it remained purely theoretical, a mathematical curiosity rather than something that could be built and tested. That changed in the 2000s, as physicists learned to create and precisely control an exotic state of matter called a Bose-Einstein condensate, when a cloud of certain kinds of atoms is cooled to temperatures within a fraction of a degree of absolute zero. The individual atoms lose their distinct identities and begin to behave as a single, coherent quantum entity described by one shared wave function. This state of matter, first created in the laboratory in 1995 by Eric Cornell and Carl Wieman, and independently by Wolfgang Ketterl, earned its creators the Nobel Prize in Physics in 2001. A Bose-Einstein condensate turns out to be an almost ideal medium for testing Unruh's analog gravity idea. because sound waves, in this context called phonons, travel through it at a well-defined, controllable speed. And because the condensate's flow can be engineered and shaped with remarkable precision using lasers and magnetic traps, in 2014, and in a series of increasingly refined experiments through the 2010s and into the 2020s, the physicist Jeff Steinhauer and his collaborators at the Technion in Israel built exactly this kind of system. A Bose-Einstein condensate engineered to flow faster than its own speed of sound in one region, creating an artificial sonic event horizon. They then looked for a signature that would confirm whether this analog black hole was producing something equivalent to Hawking radiation, in the form of correlated pairs of phonons, sound quanta, appearing on either side of the sonic horizon. In 2019, Steinhauer's group reported detecting exactly this kind of correlation, along with signatures consistent with what is called stimulated Hawking radiation, and their results have added meaningful experimental support to the theoretical framework Hawking and Unruh developed decades earlier. It is important to say plainly that this is not a literal black hole, and it is not literal proof that astrophysical black holes emit Hawking radiation in exactly the way theorists predict. It is an analog system, and the physics community continues to debate exactly how much these condensate experiments can tell us about real gravitational horizons. But it is real, measured physics, not speculation. And it depends entirely on the fact that sound in this quantum fluid has a genuine, measurable speed that plays the same mathematical role that the speed of light plays for gravity. This is where our two ideas start to connect. On one hand, we have zero-point fluctuations, confirmed by the Casimir effect and atomic spectroscopy, showing that even the vacuum of ordinary space has structure and is not featureless nothingness. On the other hand, we have analog gravity experiments, showing that in an appropriately engineered quantum medium, something behaving exactly like sound can propagate with a well-defined speed, and that speed can play the mathematical role of a universal speed limit within that system, the same role the speed of light plays in our universe as a whole. The imaginative leap explored by some theorists, and the leap this documentary is built around, asks whether these two ideas might be two views of the same deeper truth, whether the vacuum of our own universe, filled with its zero-point fluctuations, might itself behave in some ways like an underlying medium, with something like an intrinsic elasticity that ultimately sets the speed at which disturbances, including light itself, can propagate before going further. It is worth remembering just how hard won our confidence in the speed of light actually was, because that history shapes how physicists think about the idea of it being an emergent quantity rather than a bedrock constant. For most of antiquity and well into the scientific revolution, many natural philosophers, including Aristotle, assumed light traveled instantaneously, with no finite speed at all. Galileo attempted an experiment in the early 1600s, stationing assistants with lanterns on distant hilltops and timing how quickly they could signal one another. But the speed of light proved far too fast for any such method to measure, and Galileo could only conclude that if light did have a finite speed, it was extremely high. The first real measurement came from an unexpected direction, astronomy rather than terrestrial experiment. In 1676, the Danish astronomer Ole Rømer, studying the orbital timing of Jupiter's moon Io, noticed that Io's eclipses arrived slightly later than predicted when Earth was farther from Jupiter in its orbit, and slightly earlier when Earth was closer. Raymer correctly reasoned that this timing discrepancy was caused by the varying distance light had to travel to reach Earth. And from this insight he produced the first quantitative estimate of the speed of light. A figure that, while considerably less accurate than modern measurements, correctly established for the first time that light's speed, though enormous, was finite rather than infinite. Later refinements, including work by the English astronomer James Bradley in the 1720s using the phenomenon of stellar aberration, and eventually far more precise, terrestrial, measurements in the 19th century by physicists including Hippolyte Fizeau and Léon Foucault, using rapidly rotating toothed wheels and mirrors to measure the tiny time delay of light traveling known distances on Earth, steadily converged on the value we use today, 299,792,458 meters per second, a figure now treated as an exact, defined constant since 1983, when the meter itself was redefined in terms of the distance light travels in a fixed fraction of a second, rather than the other way round. The most famous and consequential experiment in this long history did not measure the speed of light directly at all, but instead tested whether that speed depended on the observer's own motion through space, a question that mattered enormously to 19th century physicists who believed light must be a wave propagating through some invisible, all-pervading medium they called the luminiferous ether, in rough analogy to how sound waves propagate through air. If such an ether existed, then the measured speed of light should differ slightly depending on whether an observer on Earth was moving with or against the flow of the ether as our planet orbited the Sun. In 1887, the American physicists Albert Michelson and Edward Morley built an extraordinarily sensitive instrument, an interferometer, designed to detect exactly this kind of tiny difference by splitting a beam of light in two, sending the halves along perpendicular paths, and then recombining them to look for interference patterns that would reveal any difference in travel time. The results stunned the physics community. There was no detectable difference at all. Light appeared to travel at exactly the same speed regardless of the direction it was measured in, or the motion of the observer relative to the presumed ether. This null result sat as an unresolved puzzle for nearly 2 decades, prompting a range of increasingly strained attempts to rescue the ether concept, including a proposal by the Irish physicist George Fitzgerald and independently by the Dutch physicist Hendrik Lorentz that objects moving through the ether might physically contract in the direction of motion by just the right amount to make the ether undetectable. A mathematically ingenious but conceptually awkward patch. It was Einstein, in 1905, who resolved the puzzle not by patching the ether concept further, but by discarding it altogether, proposing instead that the speed of light in a vacuum is simply the same for all observers in all inertial reference frames, as a fundamental postulate of nature with no medium required at all. From that single audacious postulate, combined with the equally simple requirement that the laws of physics look the same to all inertial observers, Einstein derived the entire framework of special relativity, including the now famous relationships between space, time, mass, and energy, encapsulated in the equation relating energy to mass and the speed of light squared. It is a striking historical irony worth sitting with for a moment, that the idea explored in this documentary, the possibility that the speed of light might, after all, emerge from the properties of some underlying medium filling space, echoes the very ether concept that Einstein's relativity swept away more than a century ago. The crucial difference, and it is a genuinely important one, is that the historical ether was proposed as a classical medium, expected to have a definite rest frame that experiments like Michelson and Morley's should have been able to detect. The modern, speculative quantum vacuum medium explored by emergent gravity researchers today is a fundamentally different kind of proposal, built from quantum fields whose vacuum state, remarkably, remains the same for all inertial observers by construction, precisely because it is defined using the same relativistic quantum field theory that already incorporates Einstein's postulates from the start. Whatever the vacuum turns out to be, at the deepest level, any successful theory will have to reproduce the Michelson-Morley null result and the entire successful edifice of special and general relativity built on top of it. A formidable requirement that any candidate theory of emergent light speed must satisfy before it can be taken as a genuine advance, rather than a step backward toward ideas already ruled out by experiment. To take that idea seriously, we need to understand what elasticity even means in this context. In an ordinary material, like steel or water or air, elasticity describes how strongly the material resists being compressed or deformed, and how quickly it springs back to its original shape once the deforming force is removed. Physicists quantify this with a number called the bulk modulus, which measures the pressure needed to produce a given fractional change in volume. Steel has an enormous bulk modulus, somewhere around 160 billion pascals, which is why it takes tremendous force to compress even slightly. Water has a bulk modulus of about 2.2 billion pascals, considerably softer than steel, but still remarkably stiff for something we think of as flowing and yielding. Air, by contrast, has a bulk modulus around 100,000 pascals at normal atmospheric pressure, thousands of times less rigid than water. It is worth sitting with these numbers for a moment, because the range of values found in ordinary materials on Earth is itself instructive. Diamond, the stiffest naturally occurring material widely studied, has a bulk modulus of around 440 billion pascals, more than 2.5 times that of steel, and correspondingly, sound travels through diamond at speeds exceeding 12,000 meters per second, faster than through almost any other known substance. At the opposite extreme, a gas like helium at low pressure has a bulk modulus far below that of air, and sound moves through it comparatively slowly relative to its low density. Though because helium atoms are so much lighter than the nitrogen and oxygen molecules that make up most of air, the actual speed of sound in helium turns out to be faster than in air, close to 970 meters per second. A fact familiar to anyone who has inhaled helium from a balloon and noticed how strange and high-pitched their voice becomes, since the resonant frequencies of the vocal tract shift upward when the speed of sound in the surrounding gas increases. This interplay between stiffness and density, rather than either quantity alone, is what ultimately determines how quickly a disturbance can propagate through any medium. And it is precisely this interplay that theorists, exploring vacuum elasticity, must grapple with when they try to translate the zero-point energy density of empty space into something resembling an effective stiffness and an effective inertia for the vacuum as a whole. The speed of sound in any of these materials depends directly on this stiffness. Along with the material's density, the stiffer the material relative to its density, the faster sound travels through it, because a disturbance at one point is transmitted almost instantly to neighboring regions when the restoring forces are strong. This is why sound moves through steel at around 5,900 meters per second, more than 17 times faster than through air. where sound travels at roughly 343 meters per second at typical room conditions. Water sits in between, carrying sound at around 1,480 meters per second. In every case, the underlying physical story is the same. A disturbance pushes molecules together, the material's internal restoring forces push back, and that push propagates outward as a wave, at a speed set by the balance between the material's stiffness and its inertia. Now, ask what plays that role in the quantum vacuum. There is no literal density of molecules to push around, but quantum field theory does give the vacuum something that functions. In certain mathematical respects, like an energy density and a pressure, arising from those zero-point fluctuations we have already discussed. This is not a loose metaphor invented for this documentary. It appears directly in the equations of general relativity through what is called the cosmological constant, a term Einstein originally introduced in 1917, removed later in life, and which modern cosmology has revived because it appears necessary to explain the accelerating expansion of the universe. Discovered through observations of distant supernova in 1998 by two independent teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees, the cosmological constant behaves mathematically exactly like a form of energy density and pressure associated with empty space itself. Observations of that accelerating expansion, along with detailed studies of the cosmic microwave background by missions including the Wilkinson microwave, anisotropy probe, and later the Planck satellite, allow cosmologists to measure the value of this vacuum energy density with real precision, arriving at a figure amounting to roughly 6 times 10 to the negative 27th kilograms of mass equivalent per cubic meter, an almost unimaginably small number, but not zero. Here is where things become genuinely strange, and genuinely important for the honest version of this story rather than the exaggerated one. When theoretical physicists attempt to calculate the expected value of this vacuum energy density directly from quantum field theory, by summing up the contributions of zero-point fluctuations across all the quantum fields we know about, up to the highest energy scales where our current theories are expected to remain valid, they get an answer that is staggeringly, almost comically larger than what is actually observed, depending on exactly where the calculation is cut off. The theoretical prediction can exceed the observed value by a factor of 10 raised to the power of 120, a number so large it dwarfs the total number of atoms in the observable universe many times over. This mismatch is known, with a certain dark humor among physicists, as the vacuum catastrophe, or more formally, the cosmological constant problem, and it stands as one of the largest, most persistent gaps between theoretical prediction and experimental measurement in the entire history of physics. This is worth dwelling on, because it tells us something important about how far our understanding genuinely extends. We know, with excellent confidence, that the vacuum possesses zero-point energy, verified through the Casimir effect and atomic spectroscopy. We know, with excellent confidence, that empty space appears to carry an intrinsic energy density that is driving the accelerating expansion of the cosmos, verified through supernova observations and cosmic microwave background measurements. But we do not currently have a working theory that correctly predicts the actual measured size of that vacuum energy from first principles. Any documentary, any article, any claim that presents a fully solved, precisely measured elasticity of the quantum vacuum, translated cleanly into a specific speed of sound through nothingness, is reaching well beyond what current physics has actually established. What we can honestly say is that the ingredients for such an idea, zero-point fluctuations, a form of vacuum energy density and pressure, and analog systems where a genuine speed of sound emerges from quantum fluctuations, are all real and separately well studied. Whether they combine into a single, unified picture of the vacuum as literally an elastic medium with a calculable speed of sound remains an open, actively researched, and genuinely unresolved question, explored through candidate frameworks that go by names like emergent gravity and analog spacetime models, rather than a solved problem with a clean numerical answer. With that honesty established, we can explore the idea itself, because even as an open question, it is a remarkably rich one, and pursuing it tells us a great deal about how physicists actually think about the deeper structure of reality. The Emergent Gravity Research Program, associated with physicists including Ted Jacobson, whose 1995 paper derived Einstein's field equations of general relativity starting from thermodynamic principles applied to local event horizons, and later Eric Verland, who in 2010 proposed that gravity itself might not be a fundamental force at all, but an emergent phenomenon arising from the statistical thermodynamic behavior of underlying microscopic degrees of freedom, much the way the pressure of a gas emerges from the statistical behavior of countless individual molecules, even though no single molecule possesses pressure on its own. In this family of ideas, space-time itself, along with gravity, would not be a fundamental ingredient of reality, but something that arises, or emerges, from a more basic quantum substrate, in a way that some researchers have compared, loosely, to how the smooth behavior of a fluid emerges from the chaotic motion of countless individual molecules, even though no single molecule has anything like fluid properties on its own. It is worth walking through Jacobson's argument in a little more detail, because the way he arrived at Einstein's equations is genuinely one of the more elegant pieces of reasoning in modern theoretical physics, even though it remains a proposal rather than an established result. Jacobson began not from the geometry of spacetime, as Einstein originally did, but from thermodynamics, the branch of physics dealing with heat, entropy, and energy flow, and specifically from a result developed earlier by Jacob Bekenstein and Stephen Hawking concerning black holes. In the early 1970s, Bekenstein had proposed, and Hawking's calculation of black hole radiation later confirmed, that a black hole possesses a genuine physical entropy, proportional not to its volume, as entropy usually is for ordinary matter, but strangely to the surface area of its event horizon, and that it possesses a genuine physical temperature as well, related to the surface gravity at its horizon. This relationship, now called the Bekenstein-Hawking entropy formula, treats a black hole as a thermodynamic object in every meaningful sense, obeying its own version of the laws of thermodynamics. Jacobson's insight in 1995 was to ask what would happen if this same entropy area relationship were assumed to hold not just for black hole horizons specifically, but for every possible local horizon in space-time, including the small, temporary horizons that a rapidly accelerating observer would perceive around themselves. A related phenomenon called the Unruh effect, first predicted by William Unruh in 1976, in which an accelerating observer in ordinary flat, empty space perceives what an observer at rest would call the vacuum as instead, containing a faint bath of thermal radiation, with a temperature proportional to the observer's acceleration. Applying the ordinary thermodynamic relationship between heat, entropy, and temperature to every such local horizon throughout space-time, and requiring the result to hold consistently everywhere. Jacobson showed that Einstein's field equations of general relativity, the equations describing how mass and energy curve spacetime, could be derived as a direct mathematical consequence, rather than needing to be assumed as a separate, independent postulate the way Einstein originally introduced them in 1915. In other words, gravity, in Jacobson's framework, is not a fundamental force at all, but something closer to a bookkeeping consequence of thermodynamics applied consistently to the fine-grained, presumably quantum, degrees of freedom hidden within every patch of spacetime. In the same way, the ordinary laws of thermodynamics governing gas pressure and temperature are themselves consequences of the statistical behavior of enormous numbers of individual molecules, even though no one doubts that gas pressure is real and useful to calculate with. Whether or not you ever think about the molecules underneath it, this line of thinking connects to another major theoretical development from the same era. The holographic principle, proposed independently in the early 1990s by Gerard T. Hooft and further developed by Leonard Susskind, building directly on the strange area-based scaling of black hole entropy that had puzzled physicists since Bekenstein's original work. The holographic principle suggests, in its boldest form, that all of the physical information contained within any region of space, including the full three-dimensional detail of everything happening inside that region, can, in principle, be encoded on the region's two-dimensional boundary, much like a hologram encodes a full three-dimensional image on a flat two-dimensional surface. If this principle holds generally, and a specific, mathematically rigorous version of it was demonstrated in a simplified but instructive theoretical model by Juan Moldacena in 1997, in what is now called the ADS-CFT correspondence, one of the most heavily studied results in theoretical physics over the past 3 decades. Then the three-dimensional space we experience, along with everything happening inside it, including gravity itself, might be better understood as an emergent, almost illusory construction arising from a more fundamental description living on a lower dimensional boundary. A description that, notably, does not include gravity as one of its ingredients at all. Eric Verland's 2010 proposal that gravity is an emergent, entropic force drew direct inspiration from this holographic line of thinking, treating gravity not as a fundamental interaction transmitted by some fundamental particle, the way the other 3 known forces are, but as a statistical tendency, similar to the tendency of a stretched rubber band to contract, arising from the way information is organized and distributed across the holographic screens that Verland proposed underlie ordinary space. None of this has been confirmed by direct observation in our own universe, and the specific mathematical setting in which Maldacena's correspondence was proven. A hypothetical universe with a particular kind of negative spacetime curvature, quite different from the roughly flat, positively curved universe we actually appear to inhabit, does not translate over in any experimentally confirmed way to the real world. But the fact that gravity, entropy, information, and the geometry of horizons keep turning up together in independent lines of research pursued by different physicists, using different mathematical tools across more than 2 decades, is treated by many in the theoretical physics community as a meaningful clue, even in the absence of direct experimental confirmation, that spacetime itself may indeed be a derived, emergent structure rather than the fundamental stage physicists once assumed it to be. A conclusion that, if it holds up, would sit remarkably well alongside the picture of an elastic, structured quantum vacuum this documentary has been exploring throughout. If this general picture turns out to be correct, and it remains a minority position within theoretical physics, actively debated and not yet confirmed by any experiment, then it becomes natural to ask whether space-time itself might possess something analogous to elastic properties, in the same sense that a fluid possesses elastic properties, even though its constituent molecules do not. Some theoretical work in this area, including research into what are sometimes called analog space-time models, deliberately borrows the mathematics of elastic media and fluid dynamics to describe how small perturbations propagate through a proposed quantum space-time substrate. In these frameworks, the speed of light itself is reinterpreted, not as a fundamental postulate imposed from outside, but as an emergent property, playing a role mathematically similar to the speed of sound in an ordinary elastic medium, arising from the underlying stiffness and density of whatever more fundamental structure space-time is built from. This is a genuinely interesting reframing, actively pursued by a real, if relatively small, community of theoretical physicists, but it remains firmly in the realm of hypothesis. No experiment has confirmed that space-time has an underlying substrate in this sense, and competing approaches to quantum gravity, including string theory and loop quantum gravity, describe the fundamental nature of space-time in quite different terms, without necessarily invoking this elastic medium picture at all. It is worth pausing here to notice something almost poetic. The specific idea that a fundamental speed limit might emerge as something like a speed of sound within a deeper medium is not, on its own, a wild or unprecedented kind of claim in physics. We have direct, laboratory-confirmed precedent for exactly this kind of relationship. In the Bose-Einstein condensate analog gravity experiments we discussed earlier, in those systems, the speed of sound within the condensate genuinely does play the mathematical role of light speed within that analog universe, setting the boundary beyond which no signal, no phonon, no ripple in the condensate can propagate back against the flow. Nobody disputes that this analogy works remarkably well, precisely because both systems, general relativity and the acoustic behavior of a quantum fluid, are described by very similar mathematical structures, a fact sometimes called universality in physics, where very different physical systems obey the same underlying equations. The open question, the genuinely unresolved frontier, is whether our own universe's fundamental speed limit, the speed of light, similarly emerges from some deeper, currently unknown medium, the way the speed of sound in a Bose-Einstein condensate emerges from the properties of the condensed atoms, or whether the speed of light truly is a fundamental, irreducible feature of reality with no deeper explanation required, as it is treated in the standard framework of special and general relativity that has passed every experimental test thrown at it for more than a century. We do not currently know the answer. What we can say, honestly and precisely, is what a genuine measurement program in this area actually looks like, because it does exist, even if it looks quite different from a single dramatic experimental announcement. Researchers working in precision metrology continue to refine measurements of the Casimir force at ever smaller separations and with ever more exotic geometries, testing quantum field theories, predictions about vacuum fluctuations to increasing precision. Researchers working with Bose-Einstein condensates continue to refine their analog gravity experiments, probing the details of analog, Hawking radiation with greater statistical confidence and exploring related phenomena like analog cosmological particle production, in which the rapid expansion of a Bose-Einstein condensate is used to mimic, in miniature, the particle creation that some theories predict occurred during the rapid expansion of the early universe. Researchers working on the cosmological constant problem continue to search for a theoretical framework that might explain why the observed vacuum energy density is so many orders of magnitude smaller than naive quantum field theory calculations predict. Exploring ideas including supersymmetry, which, if confirmed at particle accelerators, would provide partner particles, whose zero-point fluctuations could partially cancel out those of known particles. An anthropic reasoning associated with physicists including Steven Weinberg, which suggests that the observed value might be one of many possible values across a vast landscape of universes, and that we necessarily find ourselves in a universe where the value is small enough to allow galaxies, stars, and observers like us to exist at all. None of these research programs has produced a definitive answer yet. All of them represent real, ongoing, funded scientific work, published in peer-reviewed journals, conducted by working physicists at institutions around the world. If a genuine breakthrough in this area were eventually achieved, if physicists someday developed a well-tested theory correctly predicting the observed vacuum energy density from first principles, or a confirmed framework showing that spacetime genuinely emerges from a more fundamental substrate with calculable elastic properties, the implications would ripple across nearly every corner of physics. The cosmological constant problem is not a minor footnote. It sits at the intersection of quantum field theory and general relativity, two of the most successful theories in the history of science. And the fact that they conflict so dramatically over the energy of empty space suggests that our understanding of one or both of them remains incomplete at some deep level. Solving it convincingly would likely require, or produce, real progress toward a full theory of quantum gravity, unifying our understanding of gravity with the quantum framework that successfully describes the other three fundamental forces. It might also reshape our understanding of the universe's ultimate fate, since the vacuum energy density through the cosmological constant is the primary driver of the accelerating expansion that current data suggests will continue indefinitely, gradually pulling galaxies apart and eventually leaving the observable universe cold, dark, and increasingly empty over timescales measured in trillions of years. A scenario sometimes called the heat death of the universe. There is also a more speculative, forward-looking thread worth mentioning honestly as speculation rather than established science. Some researchers and engineers have wondered, mostly in early-stage theoretical work, whether a deeper understanding of vacuum fluctuations might eventually open genuinely new technological possibilities beyond the already real and useful applications of the Casimir effect in nanotechnology. Ideas along these lines include exploring whether engineered vacuum states, sometimes called squeezed vacuum states, which are already used in extremely sensitive instruments like the LIGO gravitational wave detector to reduce quantum measurement noise below what naive theory would suggest is possible, might someday be extended or generalized in ways that manipulate the propagation of signals or energy through space in novel ways. It is important to state clearly that this remains firmly in the domain of early-stage research and informed speculation, not a near-term or even clearly foreseeable technology, and any confident claims about tuning the vacuum for energy transmission or exotic propulsion belong to the speculative edge of physics, discussed by some theorists as an interesting possibility worth investigating, rather than to any established or emerging engineering discipline. The one piece of this speculative thread that has already become real, working technology deserves a closer look, because it shows how a genuinely strange quantum idea can travel from a theoretical curiosity to an operating instrument in a matter of decades. Ordinary quantum measurement is limited by what is called shot noise, a kind of intrinsic fuzziness arising directly from the same uncertainty principle responsible for zero-point energy in the first place. When you try to measure something as delicate as the tiny stretching and squeezing of space, caused by a passing gravitational wave, the quantum fluctuations of the laser light you use to make that measurement introduce their own noise, ultimately setting a hard floor on how precise the measurement can be, a floor that seemed, for a long time, to be an unavoidable law of nature. But the uncertainty principle only constrains the product of the uncertainty in two complementary quantities, not each one individually. This means it is possible, in principle, to engineer a quantum state of light, called a squeezed state, first proposed theoretically in the 1970s and demonstrated experimentally in the laboratory in the mid-1980s, in which the uncertainty in one property of the light, the one relevant to a particular measurement, is deliberately reduced below the ordinary quantum limit, at the cost of increasing the uncertainty in a different, irrelevant property. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, which made the first direct detection of gravitational waves in 2015, an achievement recognized with the Nobel Prize in Physics in 2017 for Rainer Weiss, Barry Barish, and Kip Thorne, began incorporating squeezed light technology into its detectors during upgrades in the second half of the 2010s, allowing the instrument to detect gravitational waves from more distant, fainter sources than would otherwise have been possible using ordinary laser light alone. What makes this relevant to our larger story is that squeezed light is not simply a clever engineering trick bolted onto an otherwise classical instrument. It is a direct, practical application of manipulating the quantum vacuum itself, since the noise being reduced originates from vacuum fluctuations entering the interferometer through its otherwise unused ports, and squeezing works by engineering the quantum correlations of those vacuum fluctuations before they ever reach the detector. In a very real sense, every gravitational wave LIGO has detected using its upgraded, squeezed light configuration was measured with the help of a deliberately engineered, carefully sculpted piece of quantum vacuum, a small but genuine example of physicists learning to shape the texture of nothingness itself for a practical, scientific purpose, decades before any grander vision of vacuum engineering could be realized, if it ever can be at all. This connects to a broader and increasingly important story in modern physics: the rise of quantum information science as a serious experimental discipline. Concepts that once lived purely in the abstract mathematics of quantum field theory, including entanglement, superposition, and the delicate manipulation of vacuum states, are now manipulated routinely in laboratories building quantum computers, quantum communication networks, and ultra-precise quantum sensors. Companies and research institutions around the world are now capable of trapping individual atoms, individual photons, and individual superconducting circuits with a level of control that would have seemed like science fiction to the physicists who first calculated the Casimir effect, or first proposed the idea of zero-point energy. This growing technical mastery over individual quantum systems is part of why questions about the deeper structure of the vacuum, once considered almost purely philosophical, have become increasingly approachable as genuine experimental physics. Every advance in our ability to control, cool, isolate, and measure quantum systems with ever greater precision is, in a small way. Also, an advance in our ability to interrogate the vacuum itself, to ask it more detailed and more searching questions, and to hold its answers up against the predictions of our theories with ever finer resolution. Before we move toward a close, it is worth slowing down and looking more closely at how physicists actually go about testing something as elusive as the structure of empty space, because the methods themselves are almost as fascinating as the results. Precision measurement of the Casimir force has become its own specialized discipline within experimental physics. The original theoretical prediction made by Casimir in 1948 involved two perfectly flat, perfectly parallel conducting plates, a configuration that turns out to be extraordinarily difficult to build in practice, because even microscopic imperfections in flatness or alignment introduce forces that can swamp the delicate Casimir signal. Experimentalists eventually found a clever workaround, replacing one flat plate with a sphere. Since the force between a sphere and a plate can be calculated with confidence from the flat plate result using a mathematical technique called the proximity force approximation, and because a curved surface is far more forgiving of small alignment errors than two flat surfaces held parallel to within nanometers. Using this configuration, along with extremely sensitive torsion balancers and atomic force microscopes, capable of detecting forces on the order of a piconewton, roughly 1/1,000,000th of the weight of a paperclip, researchers through the late 1990s and into the 2000s were able to confirm Casimir's original prediction to within a few percent, and later experiments pushed that precision even further. More recent work has explored what happens to the Casimir force when the intervening vacuum gap is replaced by different materials, or when the geometry of the plates is deliberately shaped into gratings and other patterns, testing whether the force can be tuned, and in some carefully engineered cases even reversed from attractive to repulsive, a possibility first proposed theoretically by the physicist Evgeny Lifshitz in the 1950s as an extension of Casimir's original calculation, and later demonstrated experimentally using specific combinations of materials immersed in a fluid rather than a true vacuum. All of this experimental effort matters for our story because it establishes, with growing precision, exactly how the zero-point structure of the vacuum responds to boundaries and geometry, which is precisely the kind of detailed, quantitative information any future theory of vacuum elasticity would need to match. On the cosmological side, the observational effort to pin down the properties of vacuum energy has become one of the largest coordinated projects in modern astronomy. The original 1998 discovery of accelerating expansion relied on measurements of Type 1a supernova, a class of stellar explosion that reaches a remarkably consistent peak brightness, making them useful as what astronomers call standard candles, objects whose true brightness is known well enough that their distance can be calculated from how bright they appear from Earth, by comparing those distances to the redshift of the light, which reveals how much the universe has expanded since the light was emitted. The two research teams, one led by Saul Perlmutter and the other jointly led by Brian Schmidt and Adam Rees, independently found that distant supernova appeared fainter and therefore farther away than a universe with only matter and no additional vacuum energy would predict. The implication was that the expansion of the universe is not slowing down under its own gravity, as had been the leading assumption for decades, but speeding up, and the simplest explanation, adding a vacuum energy term to the equations of general relativity, exactly reintroduced Einstein's long-abandoned cosmological constant, though for a completely different reason than Einstein originally proposed it. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. And since then, the effort to measure vacuum energy, more commonly referred to in cosmology as dark energy, has expanded dramatically, involving the Wilkinson microwave anisotropy probe and the Planck satellite mapping the cosmic microwave background, the Sloan Digital Sky Survey and the Dark Energy Survey mapping the large-scale distribution of galaxies, and more recently the Dark Energy Spectroscopic Instrument, which has been building an extraordinarily detailed three-dimensional map of tens of millions of galaxies, specifically to track how the expansion rate of the universe has changed over cosmic history. Results released in the mid-2020s from this newer survey have even suggested, though not yet conclusively confirmed, that the density of dark energy might not be perfectly constant over cosmic time as the simplest cosmological constant model assumes, but might instead be evolving slowly, an intriguing hint that, if it holds up under further scrutiny and independent confirmation, would suggest the vacuum energy of our universe is not a fixed, unchanging quantity but something with its own dynamics, changing gently as the universe itself evolves. It is worth explaining in a little more detail exactly how an instrument like the Dark Energy Spectroscopic Instrument, usually referred to by its acronym, manages to detect something as subtle as a slow drift in the density of dark energy over billions of years. The instrument sits atop the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona, and its defining feature is an array of 5,000 small robotic positioners, each one capable of aiming a thin optical fiber at an individual galaxy with remarkable precision, allowing the instrument to capture detailed spectra, essentially a fingerprint of the light, from 5,000 galaxies simultaneously during a single observation. By measuring the redshift of each galaxy, the degree to which its light has been stretched toward longer, redder wavelengths by the expansion of the universe during its journey to Earth, and by combining these redshifts with the galaxy's positions on the sky, researchers can build an enormous three-dimensional map of the universe's large-scale structure, stretching back across more than 10 billion years of cosmic history, buried within the subtle statistical pattern of how galaxies are clustered throughout. This map is a faint but measurable signature called baryon acoustic oscillations, essentially fossilized sound waves that rippled through the hot, dense plasma of the very early universe before recombination, the moment roughly 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and light to travel freely for the first time. These ancient sound waves left a preferred separation distance imprinted on the distribution of matter, a kind of cosmic ruler with a known physical length. And by measuring how that ruler's apparent size changes at different distances, and therefore different points in cosmic history across its enormous galaxy catalogue, the Dark Energy Spectroscopic Instrument can trace out, with real statistical rigor, exactly how quickly the universe was expanding at each stage of its history, and therefore exactly how the density and behavior of dark energy have evolved over time. The initial results, released in stages beginning in 2024 and continuing through 2025 and into 2026, combining the instrument's own galaxy survey data with independent measurements of the cosmic microwave background and with the original Type 1a supernova technique that first revealed accelerating expansion back in 1998, have shown a mild but persistent preference at a statistical significance that has grown but not yet reached the very high confidence threshold physicists typically require before declaring a genuine discovery. 4 models in which dark energy is not perfectly constant but weakens gradually over cosmic time. If this trend is confirmed by further data, and the collaboration continues, collecting observations with the explicit goal of testing exactly this question with ever greater statistical power, it would represent one of the most significant developments in cosmology since the original, because a genuinely evolving dark energy density would be extremely difficult to explain using the simplest cosmological constant picture, in which vacuum energy is treated as an absolutely fixed, unchanging property of empty space, and would instead point strongly towards some kind of dynamical field or evolving physical mechanism underlying the acceleration of the universe. A mechanism the theorists have already begun exploring under names including quintessence, a hypothetical dynamical energy field distinct from the vacuum energy of quantum field theory, whose value and behavior could naturally change as the universe expands and cools. This last point connects back to our central theme in an unexpected way. If vacuum energy can change over cosmic time, however slowly, that itself is a clue about its underlying nature. A truly fundamental constant, built into the bedrock of physical law with no deeper explanation, would not be expected to drift, but a quantity that emerges from some deeper physical process. The way the pressure of a gas emerges from the statistical behavior of its molecules and can therefore change as the gas is compressed or heated, might well be expected to evolve as the conditions of the universe itself evolve, confirming or ruling out this kind of drift, an effort actively underway right now, through ongoing observations from the Dark Energy Spectroscopic Instrument and planned future missions, including the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, could turn out to be one of the most important pieces of evidence bearing on whether the vacuum truly behaves like a dynamic, elastic medium in the deeper sense this documentary has been exploring, or whether it is simply a fixed, irreducible feature of the universe with no further explanation required. There is a broader lesson tucked inside all of this experimental effort, one that says something about how science actually makes progress on its hardest questions. The vacuum catastrophe, the staggering mismatch between the theoretically predicted and observationally measured value of vacuum energy, has now stood unresolved for the better part of a century, and it has resisted every clever theoretical attempt to explain it away. Supersymmetry, once considered among the most promising candidate solutions because it predicts partner particles whose zero-point contributions could cancel much of the problematic vacuum energy, has not yet been confirmed by any experiment at the Large Hadron Collider, despite 2 decades of searching, and if supersymmetric particles exist at all. Current data suggests they must be considerably heavier than many earlier theoretical models predicted, weakening, though not eliminating, their usefulness as a clean solution to the cosmological constant problem. String theory, another leading framework for unifying quantum mechanics and gravity, offers its own perspective on the problem through what is called the string landscape. The idea that the equations of string theory may permit an enormous number, potentially more than 10 raised to the power of 500, of distinct stable vacuum states, each with its own value of vacuum energy, raising the anthropic possibility that we simply find ourselves in one of the rare vacua, where the value happens to be small enough for complex structures like galaxies and observers to form. This idea, associated prominently with physicists including Leonard Susskind, in an earlier and more general form, Steven Weinberg, remains deeply controversial within the physics community, criticized by some as unfalsifiable and celebrated by others as the most honest available explanation given the evidence. No consensus has emerged, and it may be that a genuinely new theoretical idea, not yet proposed by anyone, will ultimately be needed to resolve the puzzle. Looking ahead, the next generation of instruments designed to probe exactly these questions is already under construction or in advanced planning. The Einstein telescope, a proposed underground gravitational wave observatory to be built in Europe, and Cosmic Explorer, a similarly ambitious proposal in the United States, are both designed to be roughly 10 times more sensitive than current detectors like LIGO, and both plan to make even more extensive use of squeezed vacuum states and other quantum-enhanced measurement techniques to push past the limits imposed by ordinary quantum noise, potentially allowing researchers to detect gravitational waves from black hole mergers occurring so early in cosmic history that the very first generation of stars had barely finished forming. On the atomic physics side, laboratories around the world continue to push Bose-Einstein condensate experiments toward ever larger systems, ever more precisely controlled flows, and ever more sensitive detection schemes, with some groups now exploring whether similar analog techniques can be extended beyond simple sonic black holes to simulate other exotic predictions of curved spacetime physics, including analogues of cosmological particle production during inflation, the extraordinarily rapid expansion many cosmologists believe the universe underwent in a fraction of a second after the Big Bang, and analogues of the physics surrounding rotating black holes, which possess their own distinct and mathematically richer horizon structure compared to the simpler, non-rotating black holes most laboratory analogues have focused on so far. Meanwhile, space-based missions, including the Laser Interferometer Space Antenna, a joint European Space Agency and NASA project expected to launch in the early 2030s, will extend gravitational wave astronomy to much lower frequencies than ground-based detectors can reach, using a constellation of spacecraft separated by millions of kilometers and connected by laser beams, opening an entirely new observational window on events, including the mergers of the supermassive black holes that sit at the centers of colliding galaxies. Each of these instruments, in its own way, is a tool for listening more closely to the deep structure of spacetime and the quantum vacuum threaded through it, extending the same basic scientific lineage that began with Casimir's plates, Unruh's sonic horizons, and Perlmutter, Schmidt, and Ries's fading supernova, a lineage built entirely from careful measurement rather than speculation, patiently accumulating evidence about a question that remains, even after a full century of quantum physics, genuinely and honestly unresolved. It is worth returning one more time to the Bose-Einstein condensate laboratories, because they offer a useful and grounding reminder of just how far careful, patient experimental work can take an idea that begins as pure theoretical speculation. When William Unruh first proposed the mathematical analogy between sonic horizons in flowing fluids and event horizons around black holes in 1981, there was no clear experimental path forward. The technology to create and precisely manipulate a Bose-Einstein condensate did not yet exist. It took more than 3 decades of steady technological progress in laser cooling techniques pioneered by physicists including Stephen Su, Claude Cohen-Tanuji, and William Phillips, who shared the 1997 Nobel Prize in Physics for their work, and in the broader development of atomic and optical physics, before Jeff Steinhauer's team was able to build a system precise enough to actually test Unruh's decades-old proposal in the laboratory. That kind of patient, incremental technological development, often driven by researchers with no direct connection to the original theoretical proposal, is how genuinely difficult physics questions eventually get answered, and it offers a reasonable template for how the deeper questions about vacuum elasticity explored in this documentary might eventually be resolved as well. Not through a single dramatic breakthrough announced overnight, but through decades of steadily improving precision measurements, incremental theoretical refinements, and the occasional unexpected experimental surprise that reshapes the entire conversation. What is not speculative, and what deserves real emphasis, is how much this entire line of inquiry has already changed the way physicists think about the nature of empty space, and by extension, about the nature of reality itself. For most of the history of physics, going back to the ancient Greek atomists and continuing through Newton, empty space was conceived of as a passive backdrop, a container with no properties of its own, existing only to hold matter and energy. The confirmed reality of zero-point fluctuations, the measured Casimir effect, the observed accelerating expansion driven by vacuum energy, and the laboratory demonstrated behavior of analog gravity systems have collectively dismantled that picture. Empty space, in the modern physical understanding, is not a passive stage. It is an active participant in the drama of the universe, possessing energy, exerting measurable forces, and behaving, in carefully engineered laboratory analogues at least, remarkably like a physical medium with its own internal dynamics. Whether that medium possesses something we could honestly call a speed of sound, in the same rigorous sense that air or water or steel does, remains genuinely open. The mathematics of some emergent gravity and analog spacetime frameworks suggests it might, in a deep and elegant sense, connecting the speed of light to an underlying stiffness of reality itself. The unresolved cosmological constant problem reminds us how far our calculations still are from matching observation, when we try to work out the actual numbers involved. And the remarkable, hard-won success of Bose-Einstein condensate experiments shows us, in miniature and under carefully controlled laboratory conditions, exactly what such a picture would look like if it turned out to be true. A universe where the ultimate speed limit is not an arbitrary constant handed down from outside physical law, but something that emerges naturally from the deep, quantum texture of the medium we live inside. The honest scientific position, the one worth carrying away from this exploration, sits comfortably between two extremes. It is not correct to say that the vacuum is empty, silent nothingness, unmoving and featureless, the way classical physics once assumed. Decades of confirmed experimental results, from the Casimir effect to the accelerating expansion of the universe to functioning laboratory analog gravity systems, have closed the door on that picture permanently. But it is also not yet correct to say that physicists have measured a definitive speed of sound through the vacuum of our universe in the way this documentary's premise imagines, or that the speed of light has been conclusively shown to emerge from a calculable underlying elasticity of spacetime. That remains one of the most tantalizing open frontiers in fundamental physics, sitting at the unresolved seam between quantum mechanics and gravity, pursued through real experiments in ultra-cold atomic physics, real precision measurements of subtle quantum forces, and real theoretical work attempting to explain why the energy of nothing is so peculiarly, stubbornly small. What we can say with confidence is this: the next time someone tells you that space is empty, you now know enough to gently push back. Space is filled at every point with a restless quantum activity that never fully switches off. A fluctuating structure that leaves fingerprints on the world we can measure. From the faint attraction between two metal plates placed close enough together, to the gentle, relentless acceleration pulling every galaxy in the universe apart from every other galaxy, to the carefully engineered clouds of ultra-cold atoms in laboratories on Earth where physicists have built miniature universes, complete with their own working speed of sound, and their own working analog of an event horizon. In order to test ideas that started as a strange thought experiment more than 4 decades ago, return, for a moment, to that original image of screaming in the vacuum of space, certain that no one and nothing could ever hear it. That much remains true in the way it was always meant. Sound, in the ordinary sense, the mechanical vibration of molecules bumping into their neighbors, genuinely cannot cross the near-perfect emptiness between the stars, because there are no molecules there to do the bumping. But everything explored across this documentary has been quietly building toward a different, deeper version of that same scene. If you could somehow strip away not just the air, but every last particle, every stray photon, every trace of ordinary matter, you would not find silence in any absolute sense. You would find a vacuum still humming with zero-point energy, still capable of pulling two uncrowded metal plates gently together, still carrying, in its Casimir shadow and in its accelerating pull on distant galaxies, the unmistakable signature of something with genuine physical structure. Whether that structure ever rises to the level of a true elastic medium, with a calculable stiffness and a genuine speed of sound in the rigorous sense, engineers use those words for steel or water or air, remains the honest, open question this whole exploration has circled around, refusing, deliberately, to answer with more confidence than the evidence currently allows. That refusal is not a failure of the story. It is the story. Every major idea threaded through this documentary, from Casimir's flickering virtual photons to Unruh's sonic horizons, from Jacobson's thermodynamic derivation of gravity to the stubborn, unresolved arithmetic of the cosmological constant problem, shares the same underlying character. Each one began as an idea that seemed, at the time, almost too strange to take seriously, a thought experiment scribbled on a chalkboard, a curious mismatch between two otherwise successful theories, a mathematical analogy that looked more like wordplay than physics, and each one was taken seriously anyway, tested patiently, refined across decades, and in several cases confirmed by instruments so sensitive they can register forces smaller than the weight of a single bacterium, or detect the passage of a gravitational wave that stretched the distance between two mirrors 4 kilometers apart by less than the width of a proton. That is what separates this documentary's central question from mere speculation. It is not a fantasy grafted onto real physics for the sake of drama. It is a genuine, unresolved seam in our best theories, approached the only way seems like this have ever actually been closed in the history of science, through instruments built a little more precisely than the last generation, through calculations checked a little more carefully than the last attempt, and through the plain, unglamorous persistence of researchers willing to spend entire careers chasing a signal buried in noise. So where does that leave the vacuum, and where does it leave us? It leaves the vacuum exactly where the evidence currently places it. No longer the passive, empty backdrop Newton imagined, and not yet the fully understood, precisely measured elastic medium some of today's most ambitious theorists suspect it might turn out to be, but something in between, active, structured, and only partially mapped, a genuine frontier rather than a settled fact in either direction. And it leaves us, the audience, for this small piece of an enormous ongoing investigation, with something better than a tidy answer. It leaves us with a sharper, more accurate sense of just how strange the ordinary emptiness around us actually is, and a clearer view of exactly which parts of that strangeness have already been confirmed, patiently, rigorously, and repeatedly, by people willing to spend years chasing a force too small to feel, a temperature too faint to notice, or a drift in the darkness too slow to see without a decade of data behind it. The chapter closes here, but the investigation it describes does not. Somewhere right now, a Bose-Einstein condensate is being cooled toward absolute zero in a laboratory, coaxed into flowing just past the speed of its own sound, so that a small team of physicists can watch, photon by photon, for the faint correlated whisper of an analog horizon doing exactly what unroosed equations said it should, more than 4 decades after he first wrote them down. Somewhere else, a telescope is quietly gathering the red-shifted light of galaxies billions of years old, adding one more data point to a slowly sharpening picture of whether the darkness filling the space between them is constant, or changing, or something stranger still. And somewhere in between those two efforts, in the gap between a laboratory built to simulate a black hole and an observatory built to watch the whole universe expand, sits the real, unfinished answer to the question this documentary opened with. Not whether nothing can make a sound, but how much of nothing we have already learned to hear, and how much more of it is still, patiently, waiting to be measured.